Welcome back. This is another exciting episode of Mr. Takeda Teaches Algebra. I am your host, Mr. Takeda, and I'm going to teach you some algebra right now. This is lesson 7.8 on factoring polynomials completely. This time we actually have two essential questions, factoring a four-term polynomial and factoring completely. Okay, so let's get started. The first thing we want to talk about is factoring by groupings. We have actually a new method of factoring. I'll read this to you, but then I'm going to go ahead and demonstrate it. To factor a polynomial with four terms, group the terms into pairs, then factor the GCF out of each pair of terms, and then we're going to look for and factor out common binomial factors, and this is called factoring by grouping. So I know that doesn't make a lot of sense to you, so let's do some examples here. So you'll see in the first example, x cubed plus 3x squared plus 2x plus 6, that I don't really have a common factor I can reduce this by. So remember, GCF is always the first thing we want to check, but this one doesn't have one. So what I want to do here is I want to think of this as two binomials that are added together. Okay, adding together is important. If the third term is negative, then this becomes negative. Okay, so now I'm going to factor out a common factor here. So my common factor for the first binomial is x squared. So I can think of this first side as x squared times the quantity x plus 3. For the second binomial, I can think of the GCF here as 2. And that leaves x plus 3 again. Okay, so you see what we have here. I have a common factor now of x plus 3. So now I can rewrite this as x squared plus 2. This is the x squared. This is the 2, x squared plus 2, times x plus 3. Right, x squared plus 2 times the common factor of x plus 3. Okay, let's do another one. X squared plus y plus x plus xy. I'm going to think of this as x squared. Well, let me back up here. If I think of this as x squared plus y, I won't have a common factor. So I'm going to rewrite this as x squared plus x plus y plus xy. And then out of the first term here, I can rewrite it like this. Right? I can factor out x. That's going to leave me an x plus 1. And over here, if I factor out the y, that's going to leave me really x 1 plus x, which is x plus 1 because of commutative property. So I have x plus y times my common factor of x plus 1. Okay. So that's a demonstration of factoring by grouping. Let's talk about factoring completely. As I've been saying, the first thing we always want to do is factor out the GCF. And then, can you factor by special products? Is it a trinomial square? Is it a difference of two squares? If it's a binomial, is it a difference of two squares? And then, if it's a trinomial, what type of trinomial is it? Is it simple factorable? Is it complex factorable? And then can you factor, or is it unfactorable? Can you factor it? Factoring by grouping for four terms. If we have four terms, can we factor by grouping? You can't always factor everything, but if it's four terms, can you factor by grouping? And then the most important part, always check binomials to see if they're the difference of squares. Because can we keep factoring? Can you keep factoring? That's what we mean by factoring completely. So you're going to come with binomials. You have to check and see, are they difference of squares? And if they are, then we're going to use our special products factoring methods to reduce those even further. Okay, so here's some examples. 3x cubed plus 6x squared minus 18x. And I can factor out of this 3x, it looks like, a 3x. And that's going to leave me x squared plus 2x minus 6. Okay, so I look at this trinomial and I say, well, it's not a difference of squares. This is a square, but this is not. This is negative, so it's not a square. Is it simple factorable? I need a pair of numbers that multiply to equal negative 6, but add to equal 2. So I'm thinking 6 is going to be 6 and 1, 1 and 6. That'll give me a 5 or 7. It'd be 2 and 3, which will get me a 5 or a 1. So it's not looking like I can factor this any further. So this is factored completely. One step for this one is factored completely. Okay, I cannot do this one any further. Let's take a look at the second example here. Now it looks like I have a difference of 2 squares, except this, because it's a binomial, but we'll see. The first thing I have to do is factor out GCF, right? My GCF here is going to be 7x squared, it looks like. That's going to leave me x squared minus 4. Now this is a difference of 2 squares here. So if I factor this, now here's the important part. You have to remember to always include that first GCF whenever you do any factoring for your final factored form. And of course, this is going to be x plus 2 times x minus 2. Binomials. Are either of these a difference of 2 squares? Well, this one is a sum, so we can rule that one out. This one, well, that's not a square, and this is not a square. So this one is completely factored. Like I said, just keep on checking. Can you keep on factoring? Okay, let's solve an equation by factoring completely. So what I have to do here with this example, it looks like I'm going to have to set one side equal to 0. So I'm going to call this 2x cubed plus 8x squared minus 10x equals 0. And then I'm going to factor this left side. So I can factor out 2x, and that's going to leave x squared plus 4 x minus 5 equal to 0. Okay. Now, can I factor this further? Let's see. I need a pair of numbers that multiply to equal negative 5, but add to equal 4. So that's going to be 5 and 1, right? Because 5 times 1 is 5. I want them to equal positive 4. So I want positive 5 and negative 1. 5 times negative 1 is negative 5. 5 plus negative 1 is 4. Okay. Binomials. Are either of these a difference of squares? No. So I'm done. Okay. So now the zero product property says that 2x can equal 0. X plus 5 can equal 0. And x minus 1 can equal 0. So in this case, x will equal 0. In this case, x will equal negative 5. And in this case, x will equal 1. And those are my answers. Those are my solutions. Okay. Very good. That's it for now. I'll see you in class next time. Have a great rest of your day. Bye-bye.